Welcome all. Welcome to the course on network theory. Today we are going to discuss on the topic on ABCD parameters. In the last two lectures, we have been discussing about the Z parameters and the Y parameters. So we have seen a condition where our Z parameters fails and we have gone for a Y parameter. At what condition? When our A matrix is not invertible. And when it is going to not invertible, we have taken example of a series resistor connected between the two ports, right? Then we have seen that the Y parameters, and when Y parameter exists, whenever our B matrix is invertible, right? So, and now today let us see the ABCD parameters. So before going to the actual one, let us recapitulate the two assumptions. So the first assumption is that my A is invertible. Then we can make use of our Z parameters. If not A is not invertible, if A inverse does not exist, then we are going for B matrix as invertible. So if B is invertible, we can compute our Y parameters, but this assumption might be even failed. That is, my B inverse is a singular matrix. It can be a singular matrix, right? So we cannot say that by having a Z and Y parameters are the key electrical engineering parameters. There may be cases where our Z and Y parameters are going to be lost. And one that case is that it's a component which sits outside our home and on the pole, and even it presents inside the phone charger. Here, that is, we are talking about a transformer, right? So how our transformer looks like? It is going to have two windings, and we are going to say this is primary winding and this is our secondary winding. Let us say assume that the ratio of these windings is 1:n, and if this is V1 and this is V2, right? So if it and let us assume here the current entering this particular terminal is I1 and the current leaving this particular terminal is I2. Do remember, this is the opposite convention of our two-pole network. So let us write here minus. So if you try to relate this particular four parameters, that is V1, V2, I1 and I2. So what are the two equations we can get? That is, V2 is equal to n times of V1 and my I1 is equal to minus n times of I2. Right. So from these two equations we can write our standard form. Like, let us convert this as n V1 minus V2 equal to 0, and this can be converted into I1 plus n I2 equal to 0. So let us rewrite this particular two equations. The first equation can be written as n V1 minus V2 plus 0 into I1 plus 0 into I2 is equal to 0, and here we are having 0 into V1 plus 0 into V2 plus 1 into I1 plus n into I2 equal to 0. So from this we can see that our A matrix is n minus 1, 0 and 0, and my B matrix is 0, 0, 1 and n. So you can see that my two matrices A and B are not invertible because these are singulars. So for an ideal transformer we cannot apply our Z and Y parameters. So the solution for it, we are going for another set of parameters which is known as ABCD parameters. We are going to talk about ABCD parameters, which is otherwise called as transmission parameters. We are going to say it is a transmission parameters, or simply we can say it as T parameters. Okay, So what's the main function here in Z parameters? Here current are independent and voltages are dependent, and here Y matrix current are dependent and voltages are independent. But here in ABCD transmission parameter, it tries to relate the input parameter side to the output parameters. Nothing but my V1 and I1 are the function of the output parameters. Say V1 is a function of V2 and I2, and I1 is also a function of V2 and I2. Okay, so our input and output port are directly related. Okay, so it means that to what change in output terminal will affect the input terminals values. So this will be the criteria. So the standard equation for ABCD parameters are V1 equal to AV2 minus BI2, I1 equal to CV2 minus DI2. This is because we assume that the current is leaving the terminals here, right? For example, in transformer, the current tries to leave this particular positive terminal of second output port, but in as a convention we have I2 as incoming. So in order to satisfy the convention, we try to write minus here. Okay, so these are the same thing equations which are obtained from our standard equation, that is A1 V1 plus A2 V2 plus P1 I1 plus B2 I2 equal to 0, and here we are having A3 V1 plus A4 V2 plus B3 I1 plus B4 I2 equal to 0. So we are trying to have input and output, input as one side and output as the other side, and we are trying to form this particular matrix, that is V1 I1 equal to ABCD and V2 minus I2. Do remember this minus sign is indicating that opposite of convention. Okay. Now if you try to go back to the our transformer example, so what are the equations we have? That is V1 equal to that is 1 by n V2, and I1 is equal to minus n V2, sorry, n I2. So if you try to write the equations, we are going to have a singular non-singular matrix here. Why this will be non-singular? Because if we try to rearrange or rewrite this particular equation, that is say plus 0 into I2, and here say plus 0 into V2. So we can have that here V1 I1, and we have V2 here, I2 here. So we are trying to take common here, that is V2 and I2, and the coefficient of V2 is 1 by n, and the coefficient of I2 is 0, and the coefficient of V2 is 0, and the coefficient of I2 is minus n. So my ABCD matrix is for a transformer is 1 by n, 0, 0 and minus n, which is a non-singular matrix. It's an invertible matrix. So we can conclude here that here Z and Y parameters are generally used for series and parallel circuits respectively, whereas your ABCD parameters will be used for cascading network or for a transformer. Okay. Now next question comes into our mind is that how do we compute this particular ABCD parameter for a generalized circuit, right? So that is, how do we compute? So if you try to observe this particular two equations, we can compute A and C if the second terms, that is these particular two terms, are 0. How can we make this particular two terms 0? We cannot make my B term or D term equal to 0. The only which is we have a controllable element here is the the current injected as the second port. That is, if we try to make I2 equal to 0, we will be able to eliminate these particular two terms. As a result, we will be able to compute the values of A and C. Okay, and how do we make I2 equal to 0? By trying to open the second port. Okay, now once we found B and D, our next A and C, our next objective will be how to compute or get the values of A and D here, right? So how do we get? By applying the similar principle, that is by making the first term in this equation is 0 and the first term in the second equation is 0. So how do we make? We cannot make my A parameter and C parameter equal to 0. The only way here is by making the V2 equal to 0. So if we try to make V2 equal to 0, we will be able to compute the B and D parameters. So how do we make V2 equal to 0? By short circuiting the second port. So once we try to open the second port, that is by making I2 equal to 0 so as to compute A and C, and in the next case we try to short it, that is in order to get B and D values. So if we try to do that, we are going to get A as V1 by V2 when I2 equal to 0 and C equal to I1 by V2 when my I2 equal to 0. And similarly, my B will be equal to minus V1 by I2 when V2 equal to 0 and D equal to minus I1 by I2 when my E2 is equal to 0. So how do you name these two parameters? This is a voltage gain, open circuit voltage gain, open circuit voltage gain, and this will be my short circuit current gain. What about these two? It's a short circuit. We are trying to excite at second port and we are trying to get response at the first port. So it's a reverse transfer. The ratio of voltage to current, we call it as an impedance. And what about this C? We are obtaining this C whenever we are trying to open the second port. So it's an open circuit. We are trying to excite the second port and getting the response at the first port. It's the reverse transfer. The ratio of current to voltage, we call it admittance. So we can compute these ABCD parameters in this particular way. Now, these ABCD parameters are said to be a reciprocal if, that is, a network is said to be reciprocal when my AD minus BC equal to 1. That is, determinant of my ABCD parameters, parameter matrix is equal to 1. And we are going to say a network is symmetrical if my A and D parameters are equal. So whenever my A is equal to D, we are going to say the given network is symmetrical. When our determinant of this particular ABCD parameter matrix is equal to 1, that is AD minus BC equal to 1, we are going to say the network is reciprocal. Right? So let us solve one numerical for ABCD parameters. So let us take a small example over here. What is our objective? Our objective here is to find the ABCD parameters for the given circuit and check whether the given circuit is a reciprocal or symmetrical or both. So when we are going to say my circuit is a reciprocal, when the determinant of ABCD parameter matrix is equal to 1, that is T matrix equal to 1, or when it is a symmetric, that is whenever my A parameters is equal to T parameters. So let us solve this one. So in order to get ABCD parameter, we are trying to solve using our conventional method, that is by making use of two case studies. That is, in first case study, case 1, our objective here is to find A and C parameters. So how do we obtain? When we make my second port equal to 0. So if you assume this is a black box, we will be able to compute A and C parameter when I make this AI2 is equal to 0. So if you are trying to make this I2 is equal to 0, how my circuit looks like? So whenever if I try to make this I2 equal to 0, how this circuit looks like? So we are going to have a resistor over here, and as I2 equal to 0, no current flows through it. So the total complete current goes to your 10 ohm resistor. This is my 10 ohm, and this is my 2 ohm. This is my voltage across these two terminals, and this is the I1 current entering the first port positive terminal. What about V2? As even though we are having this particular branch, the current flowing through this is 0. So the voltage drop across this 4 ohm is also 0. So the voltage across V2 will be equal to voltage across 10 ohm. So my V2 will be across here. So what we need to find? We need to find A and C. So how you are going to get the A value? A value can be written as, to remember, V1 equal to AV2 minus BI2, and I1 equal to CV2 minus DI2. Okay. So A is nothing but V1 by V2 when we make I2 equal to 0. So our objective is to find V1 and V2. Okay. So let us bring the relationship between V1 and V2. So how can we write? How can we write? Say if we try to solve this particular equation, we are going to get I1 is equal to V1 by 10 plus 2, 12. 10 plus 2, 12. But what we know? We know that V2 is equal to 10 into I1. Right? So we can write my I1 is equal to V2 by 10. So if we try to substitute over here, we get V2 by 10 is equal to V1 by 12. So if you try to rearrange this equation in this particular way, my term will be V1 by V2 is equal to 12 by 10 equal to 1.2. So my A value is equal to 1.2. So how could we find our C value? Our C value relates I1 and V2. So we already got the equation here. So the relation that is I1 and V2. So my C value will be equal to 1 by 10. Okay. So the ratio of I1 by V2, so the units are more. So this value can be written as 0.1. Now our objective is to find the values of again B and D. Okay. How do we find? By making V2 equal to 0. So these are A equal to 1.2 and C equal to 0.1. So for the second case, what we are trying to do, we are trying to short it, the second port. So when we try to short, my circuit looks something like this. Okay. Now let us say we are having a I1 current entering here, and as it's a short circuit, the I2 current will also be there. So my I2 current flows in this particular direction, and here we are going to get I1 plus I2. Okay. And what is the relation we are going to have? So in order to find the value of B, it is equal to V1 by I2, right? And we have D equal to I1 by I2. So these are obtained when my V2 is equal to 0, that is short circuited. So we need to bring a relationship between V1 and I2 and I1 and I2. Okay. Now if you try to see here, we can bring directly the relationship between I2 and I1 over here, right, by applying the current division rule. So my I2 current will be equal to the current flowing through the the opposite resistance value, that is 10 by total resistance, so 10 plus 4 into the total current I1, right? So it is I2 is equal to 10 by 14 I1, but we have assumed in general the current of I2 will be outside, inside the convention, but what we are taking, I2 is in opposite direction. So in order to satisfy this, we can write minus. So my value I1 by I2 is equal to 14 by 10 minus. So it is equal to minus 1.4. Okay, so it is minus 1.4. If you are trying to write, and if you try to change the direction from the right to left, then we are going to have here plus. So if you are assuming in the right to left, the I2 same current, we are going to have plus. So it is plus 1 by 4. So my D parameter will be equal to minus of minus 1.4, it is equal to 1.4. Now our objective is to find the values of or the relationship between V1 and I2. V1 and I2. So we know that my V1 exists between the potential difference across between these two terminals. So it's a voltage across these 2 ohm resistor and the voltage across my 10 ohm resistor. How could we write? So my V1 is equal to 2I1 plus 10 into I1 plus I2. So if we try to rearrange, we are going to have V1 equal to 12I1 plus 10I2. So we require the relationship between V1 and I2. So we should eliminate this particular term. So how do we eliminate? By making use of this particular equation, that is I2 equal to minus 10 by 14 I1. So if we try to substitute over here, so we are going to get the relationship between V1 and I2 as 6.8 ohms. So if you try to write in this particular matrix, we are going to have 1.2, 6.8 ohms, 0.1 ohms and 1.4. So we need to check whether our circuit is symmetrical or not. So what is the condition? Whenever my A equal to D, we are going to say it's a symmetrical. If you observe here, we are having A as 1.2 and D as 1.4. These are not equal. So it's not a reciprocal. But however, if you try to determinant of this particular matrix, we are going to get 1. So we can say that my network is a reciprocal circuit. So if you observe this problem solving, we can see that we have went for a large computational time, right? So we should solve these same ABCD parameters in a different way. Even though this is a circuit is very small, the computation was very much higher. So in order to avoid that, we shall go for the another way of solving this particular numerical, that is using our mesh analysis. Say let us the mesh current here be in a clockwise direction, this be I1, and this be anti-clockwise direction, this is I2. So let us write the equations. So it is V1 is equal to 2 into I1 plus 10 into I1 plus 10 into I2, right? So V1 is equal to 12I1 plus 10I2. This is my first equation. Similarly, when we try to write the second equation, that is V2 is equal to I2 is flowing for 4 ohm and 10 ohm, so it is 14 plus 14 I2, and I1 as this 10 ohm is common with the first mesh, and where the I1 current is also flowing in that particular mesh, so we are going to have 10 I1. So this is my second equation. So if you observe here, this is something looking like our jet parameters. But what we require? We require the equations in this particular form. That is V1 equal to A into V2 minus B into I2, and I1 is equal to C into V2 minus D into I2. So we require in this particular form. So if you observe carefully, we have here two currents I1, I2 and V2. And if you observe this particular second equation, we have I1, I2 and V2. So let us rearrange this equation in this particular way. So we need to require I1 in the left hand side and remaining in the right hand side. So if you try to write, it is 10 I1 is equal to V2 minus 14 I2. So if you try to bring this 10 over here or divide 10 on both sides, we get I1 equal to 1 by 10 V2 minus 14 by 10 I2. So which is nothing but I1 is equal to 0.1 V2 and 1.5 I2. So this is my C parameter and this is my D parameter. Okay, and let us see here. If you observe here the first equation, my first equation is having V1, I1 and I2. But in this first equation, what we require? V1, V2 and I2. So what is the redundant one? The redundant one is I1. So we shall eliminate this. So let us assume this is equation 3. So we shall put equation 3 in 1. We get V1 is equal to 12 into 0.1 V2 minus 1.4 I2 plus 10 I2. So if you try to multiply, we are going to have V1 equal to 1.2 V2 and we have minus 12 into 1.4 I2 plus 10 I2. So if you try to multiply this 12 into 1.4, we are going to have 16.8. So V1 equal to 1.2 V2 minus 16.8 I2 plus 10 I2. So if you try to write again, simplify it further, V1 equal to 1.2 V2 minus 6.8 I2. So if you compare with the actual equation, this is my A and this will be my B. So my ABCD matrix can be written as A, B, C, D can be written as 1.2, 6.8 ohms and 0.1 more and 1.4. So if you try to see the previous one, we got the same answer. So it means that depending upon the problem, we can use different methods to solve the same numerical or to get the same parameters. So you can observe here that whenever we are having a tree network, so we should prefer to obtain our these z parameters and convert into our parameters. And remember, we are going to discuss the conversion of one parameter to the another parameter once our S parameters is completed. And do remember, when we are having a pi circuit, we can compute the y parameters and convert into our required limit. So for T network, compute z parameters and then convert. If we have a pi network, find the y parameters, then convert. And if you observe carefully, the z parameters for T network can be found very easily. So it is 2 plus 10, we are going to have 12, that is our z11, and 10 is common for first mesh and second phase, so it is z12 and it is equal to z21 as a common, and we have the z22 as 10 plus 4, that is which is equal to 14. So once we got the z parameters for this particular T network, we can convert into any type of parameters. So do remember, these z parameters may not be exist for all these network. We are talking about here the network which is can be solved for z parameters. Okay. So what we have studied in this lecture, we have came across the ABCD parameters which was introduced. with the help of a transformer, where we have seen that our z and y parameter will not exist for an ideal transformer, and we have seen that in ABCD parameter the input port variables, that is V1 and I1, are the function of the output port variables, that is V2 and I2. And here V2 and I2 are independent, and we try to see what will be the response with the change in this particular V2 and I2 on the input port, that is V1 and I1. So V1 and I1 are dependent variables. Then we have seen the significance of our ABCD parameters, what we call A, B, C and D. A and D are voltage gain and current gain. B is impedance and C is an admittance. So it's an short circuit reverse transfer impedance, and it is an open circuit reverse transfer admittance. And next we have seen the how to find these ABCD parameters. Here we will be trying to find the A and C parameters by performing the open circuit test, and we are trying to find the parameters A, B and D by short circuit test. Both are on the second port because our V2 and I2 are independent and V1 and I1 are dependent, right? And we have seen that the circuit or a network is said to be reciprocal if my T matrix or T matrix is a determinant is equal to 1, that is AD minus BC equal to 1, and we are going to say the circuit is symmetrical if my A is equal to T parameters. Okay, then we have seen some numerical examples. How do we solve the ABCD parameter step by step? This step by step followed for how by performing our open and short circuit test, and we have even seen that this is not always will be recommendable. This depends upon the circuit we have. So if this is solved by any other method, we can solve using that and convert into the ABCD parameter equations. And we have emphasized that the importance of ABCD parameters in transmission line, and it is applicable for cascaded two-port networks. In the next lecture, we shall see the real-world applications of our ABCD parameters, and we shall solve few more numericals on it. Thank you.